I'm going to talk about a very important idea in this course, namely that of complex functions of a real variable. So since this course is about signals and systems, quite often what you're going to see in this course is that you have a signal, something like x of t, where t represents time, and something is changing as a function of time. So x of t is changing as t changes, and x may take a complex value for any given value of t. So these kinds of functions are called as complex functions of a real variable, because t typically represents time and t is usually a real variable. It doesn't make sense for time to take complex values. So one example of such a function, maybe x of t is e to the j 2 pi times t. Right? So if I set some value of t, let's say I put a value of t to be equal to one third, then x of 1/3 is simply e to the j 2 pi over 3, which is cosine 2 pi over 3 plus j times sine 2 pi over 3. Right? So that's negative 1/2 plus j times square root of 3 over 2. Now, if I plug in a different value of t, I might get a different complex number for that, right? So the way to think about this is to think of x of t as a function of time. Time is a real variable. For any given value of time, x takes a complex value, but it's changing as a function of t. And so we call this as a complex function of a real variable. So another example may be x of t is 1 over 1 plus j times 2t. That was just some example I made up. And sometimes in the course, we may see functions where the independent variable is frequency instead of time. So we may be studying phenomena where omega represents frequency, and so omega is a real variable, and something is changing as a function of frequency. So x of omega is a function. For any given value of omega, it takes some value, but that value may be a complex value. So if I set omega equal to 1, for example, I get the value 1 plus j2. So x of 1 is 1 over 1 plus j2, which is some complex number, right? And as I change omega, this number changes, and so it's another complex function of a real variable. So all signals that we are going to see in this course are typically going to be complex functions of a real variable. Now, of course, in some cases, you may just have the imaginary part to be 0, in which case it would just be a real function of a real variable, which is what you are used to seeing in your calculus courses until now. So that is just a special case of a complex function of a real variable. So everything that we are going to do with these complex functions of a real variable will also apply to functions that you have seen before. Okay. Now, let's take an example. Let's take the first example, and then I want to see how we can get some visual intuition to these functions. One thing that I'm going to emphasize throughout the course, and I think it is a good idea in an undergraduate course on signals and systems, is to get as much visual intuition as you can when you deal with signals and what is happening to these signals as much as possible. So a lot of times what you might want to do is you may want to sketch this function, right? You may want to sketch how x of t changes as a function of t. And the problem in trying to sketch x of t is that for every value of t, x of t takes a complex number. So how do you sketch something where as t changes, you have to plot a complex number for every value of t? You cannot do that on a board or a piece of paper, right? So what you have to do is one of two things. Either you have to sketch, so maybe how to sketch or draw x of t as a function of t. So you have one of two options. Either sketch the real part of x of t versus t and the imaginary part of x of t versus t. So if we do that, then clearly we can sketch the function x of t, right? It's not going to be on one plot, but you need two separate plots, one for the real part, how that changes with time, and one for an imaginary part and how that changes with time. Or the other option is to sketch the magnitude of x of t as a function of t and the angle of x of t as a function of t. So notice that the magnitude of x of t is a real valued function, right? And the angle of x of t is also a real valued function. So these two are each real valued functions of t. So we can sketch this as a function of t, and we can also sketch this as a function of t. So in either case, you're going to need two plots to be able to sketch this function. And both these are useful. Sometimes the magnitude angle versus t is useful. Sometimes the real and imaginary versus t is useful. So let's take this example and see how these plots may look like. So let's see how a sketch of the real part of x of t versus t and imaginary part of x of t versus t might look when x of t is given by e to the j 2 pi t. So let me make a little bit of space for myself here. Now we know from Euler's formula that e to the j 2 pi t is simply cosine 2 pi t plus j times sine 2 pi t, right? So what is the real part of x of t? So the real part of x of t is simply the function cosine 2 pi t, and the imaginary part of x of t is the function sine 2 pi t. So clearly we can sketch cosine 2 pi t versus t and sine 2 pi t versus t, right? If we were to sketch this, how would this look? So let's say we sketch, so this is time t equal to 0 in the middle, and the first plot is cosine 2 pi t. So cosine at 0 takes the value 1. So it's a function that goes like this. My drawing skills are not great, so it may not look symmetric, which is it's supposed to look symmetric, but you get the point, right? This is a cosine function. So at 0 it takes the value 1, and then at t equal to 1 it again takes the value 1. So this is 1/2, this is 1/4, this is 3/4, and that is 1, so on and so forth. So this is a plot of the real part of x of t versus t. In the same way, we can plot the imaginary part. And that would simply be sketching the sine function, right? So the sine function, that's going to reach its maximum. So it's going to start at 0. So it's going to go like this. So this is 0, this is 1, this is 1/2. Takes the value 1 at 1/4. So the main point is that if you want to sketch the function x of t, you're going to have to sketch the real part versus t and imaginary part versus t. Or let's see how we can sketch the magnitude of x versus t and the angle of x versus t. So let's try to do that in the bottom picture here. Let's first try to sketch the magnitude of x of t versus t. What is the magnitude of x of t when x of t is given by e to the j 2 pi t? Now when I ask students this, typically what they do is they go into Euler's formula, they look at this, and then they say, oh, the magnitude is the square of the real part plus the square of the imaginary part, and then take the square root of that. But since cosine squared 2 pi t plus sine squared 2 pi t is equal to 1, the magnitude is actually 1. That's fine, that is correct. But there is a simpler way to arrive at the exact same answer, which is to realize that this x of t is already given to you in polar form, right? And notice that x of t is 1 times e to the j 2 pi t, which means the magnitude of x of t, so this is the magnitude, and this is the angle or the phase. So the magnitude is already given to be 1, so it doesn't change with t. So plotting the magnitude as a function of time is going to be pretty easy. The magnitude is 1 and it doesn't change with t. So this is t on the x-axis and the real part on the y-axis. So here it's the magnitude of x of t versus t here. So how about the angle of x of t? So notice that the angle of x of t is given by the exponent of e without the j. So you have e to the j theta, then theta is called the angle or the phase of the complex number, right? So here you can see that the phase for any given value of t is 2 pi t. So the phase of x of t is a function that changes as 2 pi t. So let's try to plot this function. And when you try to plot something like the angle, keep in mind that we would like to plot these angles to go between negative pi and positive pi. Okay, so whenever you go outside of this bound, you want to reduce it modulo 2 pi. So you want to subtract a negative 2 pi or add a positive 2 pi to bring it back to something between negative pi and positive pi. In fact, you want to add any integer multiple of 2 pi or subtract any integer multiple of 2 pi to bring it back to within pi and negative pi. And let's try to see how this function would look. So at t equal to 0, so it takes the value 0, right? And then it starts to increase linearly until 1 over 4. At 1 over 4, it hits the value, so this is 1 over 4. At 1 over 4, it hits the value pi over 2. And then at 1/2, it hits the value pi. So it increases linearly from 0 to 1/2 to go from 0 to pi. So this is pi. So that, if you really think about what is happening here, this complex number e to the j 2 pi t. Let's think about what's happening to this complex number e to the j 2 pi t. When t is 0, the complex number is like this. As t increases, this complex number is moving along the unit circle. Why do we know it's the unit circle? Because we know that the magnitude of this function is independent of t. So no matter what the magnitude is, no matter what t is, the magnitude is 1. So it's really moving along this unit circle as t increases. So when t is 0, the complex number looks like this. T is 1/4, it looks like this. T is 1/2, it looks like this. And then as t increases further, so you're going to get something that's bigger than pi, right? It's going to continue to increase this way. But so that means we are basically somewhere here in the third quadrant. It's gone above pi. And since we would like to plot things, so angle is 0 here, it's pi here, it's negative pi here, then what we would like to do when you go above pi is to subtract a 2 pi from it to make it between 0 and negative pi. So for example, if the angle becomes say 3 pi over 2, or let's say maybe something, say 5 pi over, or let's say 7 pi over 6. So 7 pi over 6 is somewhere here. It's a little bit more than pi, right? But 7 pi over 6 is the same as 7 pi over 6 minus 2 pi, which is negative 5 pi over 6. So that's exactly what we are going to do here. So we're going to take this and we are going to subtract a 2 pi. So what happens when we subtract a 2 pi? When you subtract a 2 pi, this part is going to come down by 2 pi. So it's going to start here at negative pi and then go to 0 at 1. And then of course it goes back here. That's 1.5, and then it goes here. So the function then looks like this. So this is how the phase or the angle of x of t changes as a function of t. Now in the course, we actually have Python notebooks for you to play around with all this, where you can plot these functions and get a feel for these functions. But I've typically noticed that plotting the phase of a function as a function of t, or plotting the phase of x of omega as a function of omega, is kind of one of the harder things in the course for students to do. So I would highly encourage you to play around with the Python notebooks in the course to get a feel for what's happening here.